What if the universe was already full of time fingerprints left by evolving particles, and we've been staring at them for a century without realizing what they are? In the energy filament theory, a particle is not a rigid standard part but a dynamic filament structure propped up by the local energy sea. So when the overall tension of that sea changes, the tightness of the coil, the allowed rhythms, and the latching positions of electrons and nucleons all shift together, even though our textbooks quietly freeze them as fixed constants. Those shifts do not politely update the tables in the back of the book. They get carved into light, into abundances, into shapes and cycles across the sky, and together they form a library of time fingerprints. The most famous one is redshift. Light from distant galaxies arrives with its whole spectrum nudged towards the red, as if every line has been pulled to a longer wavelength. And in this picture, that is simply what you get when earlier, tighter electrons with slower internal rhythms emit light that still carries their slow beat while we read it with today's faster electrons and naturally conclude, this looks redder, this looks slower. Look closer at the spectra and you find that the spacing, relative strengths, and fine structures of lines can be slightly off compared with what our lab atoms produce. That is because different electron coil patterns create different energy spacings between levels, and those differences are engraved into the pattern of spectral lines, turning each distant spectrum into a sample card of how electrons were coiled back then rather than a sign that the lines went wrong. On the nuclear side, we met puzzles like the lithium problem. The universe seems to have only about a third of the lithium that standard calculations predict, which, in this language, means that in the high-tension early universe, the preferred locking angles and distances between nucleons were different. So which light nuclei could hold together and which fell apart were quietly ray-sorted. And the lithium shortfall is really a faded photograph of high-tension nuclear geometry. Molecules carry their own fingerprints as well. Measurements of bond lengths, vibration frequencies and level patterns from very distant gas clouds show tiny but persistent shifts compared with the same named molecules in Earth labs. And here that is exactly what you expect if molecular skeletons are held up by electron latch points whose angles and distances are set by the local particle rhythm. So a carbon monoxide molecule from another era becomes a slightly different epoch ruler than the one on your bench. Some of the universe's big metronomes misbehave too. Pulsar spin periods, quasar flickering patterns, and other astrophysical rhythms do not always line up perfectly with the beats our current models forecast. This makes sense if these objects are giant rhythm machines whose cycles inevitably encode the local particle timing. So when you compare their old heartbeats to the ones implied by today's particles, you hear a gentle off by a little, drifting a little that is really the slow migration of particle rhythms over cosmic time. Even the diffuse glow across the sky carries hints. In many wavelength bands, radio, infrared, and parts of the high-energy sky, the background is a bit brighter, or less uniform, than a neat, one-era universe would suggest. And in this picture, those extra layers of glow are the accumulated aftershocks of short-lived structures and stable particles shaking the sea with slightly different rhythms at different times, leaving thin coats of historical backlight on the sky. Key frequencies betray the same theme. Lines like the hydrogen 21 cm transition or the characteristic tick rates of some oscillating systems show small systematic offsets from very fine-tuned expectations, because those frequencies are literally heartbeat counts of the emitting particles. And if the particles of that era beat a little slower or faster than ours, the signal arrives with a built-in era bias. In some violent bursts, such as certain fast radio bursts or gamma-ray flashes, different energy bands sometimes arrive with strange timing offsets that go beyond what you would predict from a simple head count of electrons along the way. In this framework, that can be read as different rhythm modes, born in slightly different tension regimes, marching towards us like misaligned drum lines. So by the time they reach Earth, you see a faint layering in arrival times. When you stack all these clues together, redder starlight, drifting spectral patterns, odd element abundances, stretched molecular rulers, offbeat cosmic clocks, uneven background glowing, Biased key frequencies and layered arrival times. They span photons, atoms, nuclei, molecules, compact objects, and the cosmic background. Yet they all whisper the same sentence. Particles coiled differently in different tension environments. They keep timing differently, and those differences are stored in spectra, abundances, structures, and cycles as a sprawling fingerprint library of the universe's history. Time fingerprints are not carved into one rock or one event. They live in light, in elements, in molecular shapes, and in the rhythms of the sky, all telling us that particles have a past, that they know what era they came from, and that they have quietly written their own stories across the whole cosmos. Tap follow, share it on New Physics, Clear Universe.